Let's continue working through the steps for testing a hypothesis about a population proportion. To determine the decision rule, we now have to bring in our friend, the binomial distribution. And so here I have pictured a binomial distribution. How have I created that? Couple things. First of all, I need to know two parameters in order to construct the binomial distribution. I need to know pi, the proportion in the population, and I need to know how many observations I'm going to look at. Now, this particular binomial distribution is based upon 8 observations. How do I know? I can see that the values of x range from 0 to 8. That value of x represents the number of successes, where success simply means something that we're looking for, like treatment improvement. And so when I see from 0 to 8, I'm looking at all the possible number of successes I could have if I had some number of observations. That number is obviously 8 because it is capped at 8 as the maximum possible number of successes. Now we also have to set pi, but you say, wait a minute, pi is unknown. That's actually what we're testing about. How could we know pi? We cannot. But what we can do is establish a binomial distribution that we call under the null hypothesis, meaning we assume the null hypothesis to be true for the purposes of creating this distribution. And that's what we're doing. So the null hypothesis is that pi equals 0.5. So this is a binomial distribution created from two parameters, pi, 0.5, and n, the sample size, of 8. Now here in the right-hand margin, next to the picture of the distribution, I've actually provided the probability. And how did I calculate those probabilities? I calculated them using the binomial formula. If you have not already watched the video on the binomial distribution, take a look and you'll see how we calculate these using the binomial formula. And here, these probabilities should all add up to 1. Why? Because we have a mutually exclusive and exhaustive set of outcomes from 0 to 8 successes. Only one of these is going to happen, but one of them will happen. So, for example, the probability of having 0 successes when pi in the population is 0.5 is very small. It's 0.003906. That's 0 out of 8 of the observations showed success or no success. The same is true of the opposite end. If pi, the probability of success, is 0.5, then what's the possibility that 8 out of 8 will be successful? And that is, again, a low probability of 0.003906. You notice that right in the middle, 4 out of 8, is where we have our highest probability. It's not surprising that the highest probability is 4 out of 8, since we're hypothesizing that pi is 0.5. The probability of success is 0.5. Now we have to determine the decision rule. So how do we do that? Well, we start with the value that is most inconsistent with the null hypothesis and most in favor of the alternative. Well, the alternative says that pi is greater than 0.5. So what is most inconsistent with 0.5 and more consistent with the alternative? Wouldn't that be if everyone was successful, if you had a 100% success rate in your sample? That is, all 8 would be successful. So we are going to put that in what we call our rejection region, meaning that if we get that value, we're going to reject the null hypothesis. The probability of that is 0.003906, and all we need to do is keep the probability under 0.05. Well, this means that we can actually put 7 in the rejection region as well. 7 has a probability of 0.03125. But the way we do this is we form a rejection region in which you calculate the total probability of that region, and it stays under 0.05. Note that if I add up 7 and 8, I will still be under 0.05. Specifically, I'll be at about 0.035, and that is under 0.05. And so 7 and 8 are going to be in my rejection region. Why not 6? Well, look what happens if I add 6, 7, and 8. Then I'm well over 0.05. So what I have calculated here that I called alpha prime is I've calculated the actual probability of getting in the rejection region for this particular setup where the null hypothesis is 0.5 and we make 8 observations. The nominal rate of 0.05 is the maximum tolerance I have. If I put 7 and 8 in my rejection region, I stay under that maximum tolerance. If I add 6, I go over that maximum tolerance. So now I have a decision rule. I will reject the null hypothesis if there are 7 or 8 successes in these data. And now I do the final step. I make observations, align this with the decision rule, and decide whether to retain or reject the hypothesis. For our purposes, let's suppose we had 6 successes. Well, if I have 6 successes, you know from our decision rule that we just made that we cannot reject the null hypothesis. We must retain the null hypothesis. And so therefore, I will end my hypothesis testing with a conclusion. I retain, I cannot reject the hypothesis. Notice I didn't use the word I accept the null hypothesis. That would be silly to accept the null hypothesis because it says we will have 50% success. Well, in 8 observations, 50% success would be 4. I got 6. I was above 0.5 successes for my sample, but it's not enough evidence to conclude in my population that pi is greater than 0.5. And that's what it's all about. Do I have enough evidence to say with 95% confidence? Why 95%? Because I set my maximum type 1 error rate at 5%. So do I have enough evidence to say with 95% confidence that pi is greater than 0.5 in the population? I do not. And then we can take a step we call creating a p-statistic, and that p-statistic is made up of the probability we had before we collected these data of obtaining what we actually observed and things that are more inconsistent with the null hypothesis. In this case, what we observed was 6. What would be more inconsistent with the null hypothesis? 7 or 8. If you add up 6, 7, and 8, that gives you your p-statistic. This is not a probability. We've actually already collected the data. Probability is about what could happen, and we're done. So the p-statistic is not a probability, but it does say something to us about where our observations fell and whether or not we got an observation that was in the rejection region. Let's also not forget to talk about the effect size here. What was our actual effect size? That is, of the 8 individuals, how many were helped by the treatment? 6. So the effect size, pi hat, is 0.75. What happened in the sample is encouraging. So I come away from this study saying a couple things. One is, it looks like my treatment may work because 75% of the individuals in my sample were helped by the treatment. However, I do not have enough evidence to say that it would work to that same extent in the population, and more specifically, that more than 50% of individuals in the population would be helped. We have our descriptive statistic that is encouraging. We have an inferential statistic that says, yeah, we're encouraged, but the stability of that statistic may be such, or rather the instability, that in fact, we may not get this same kind of result if we were to do this study again. We really would like to see if we could reject the null hypothesis and confirm that not only will the treatment work in the sample, it will work in the larger population, at least work for over 50% of the individuals in the population. So to summarize, using the binomial distribution to test a hypothesis about a population proportion requires very few conditions for valid inference, and exact probabilities can be used for the test. Any data can be transformed to dichotomous data, so the test of a hypothesis about a population proportion can be applied to a wide variety of research questions. Even if you have a continuous measure, you could create a cutoff point and dichotomize individuals, and then see what proportion of individuals in your sample exceed the particular value, and determine if that's enough to confirm that the proportion in the population that would exceed the cutoff is a certain amount. Some of the best alignment with the research intent may come from dichotomous data, so I consider this a useful test. And then, as we'll see in an upcoming video, a confidence interval can be constructed by testing all hypotheses.